Hi, so I'm Dan. Liberzon is the last name. I'm from civil engineering, and the lab is called TSAIL for Technion Sea Atmosphere Interactions Research Laboratory. Now, we do a variety of things. Before I will explain what we do and how some of the things are connected to the program, these are the ways to contact me. There's an internet site, there's a QR code. Will keep appearing in the next slides also, so you don't lose me. So what's the main idea of our research projects? We study environmental flows in the basics. We focus on waterways, the water flow induced by the waterways, the interaction of this water surface flows, waves and the flow with the wind, with the atmospheric turbulent flows, and the atmospheric turbulent flows in different interactions also. We dwell deep into the interactions between wind and vegetation, the structure of turbulent flows. And why are we doing this? We're doing this for several reasons. The first main reason is because we want to know how it works. However, there are some very interesting applications of this knowledge. Some of this knowledge is going toward creating, for example, autonomous navigation in the sea and in the air. We do not deal with land navigation, right? Risk predictions in working in coastal and open sea areas. Of course, it has applications in weather and climate forecasting, autonomous irrigation. One of our works on evaporation worked on this, and prediction of extreme events, which is connected to all of this. Now, how from this basically physical research, and we're doing experimental research, how can we get to these applications? We need to develop technologies that will allow us to collect enough and good enough data on these problems that can then be translated into signals, into databases, into libraries, and into algorithms that will allow any of these applications. So we are constantly working on developing spatio-temporal data of this phenomena, collection of them, or measurement of such data, the real-time products of such data, and we naturally use various statistical and spectral models that can then be run to create forecasts, short-term and long-time predictions. Now, the tools that we use to do this research, right, to get between the applications, to create the applications, we want to create these measuring technologies, and the tools for these technologies are twofold. On one side, we work on inventing new sensors and new probes. Sensor is something that can sense something. Probe in this context is something that can have one or several sensors and basically produce the data that we need. Some recent works include remote sensing of waves by polarized light, sensing of turbulent wind variations by heat transfer, high fidelity evaporation sensors, which I mentioned for autonomous irrigation, electric mesh droplets counter that we started developing now. And it also forces us to work a lot in data processing, traditional methods and AI-based methods also. So before showing you two examples, I want to jump to the more important part of this talk. I'll show the examples. This is what's important to the students. And we are looking for great students, good students, excellent students, any good students, right? So I just wanted to show you a little bit of images. In all of these images, we're all smiling. You will not see us sad in these images because this is how we work in the lab. And you can see that, for example, during the last decade approximately, out of 12 master graduates, 5 decided to stay for PhD. Out of 6 PhD graduates, 5 continued to postdocs. I call it that they basically work in good environment, researching various aspects of environmental fluids, right? So now about two examples. One example is the latest one. It was published just a couple of months ago. This is a new remote, well, it's slightly obstructed.
I think you can just press on the, just below on the, no.
Yes. Thank you. So it's an AI-based remote sensing system for waterways. Although appearing pretty simple, before this system, we didn't possess any tool, sensor, probe to create accurate spatio-temporal, meaning in space and time together, and phase resolve, measurement of the two-dimensional water waste field propagating through the open ocean or in coastal areas. We do have some other technologies that can create time variations in specific space, or some space variations, spare images, and so on. But we didn't have any system that can connect them, be accurate, and be phase resolved, meaning fast enough in time and at high enough resolution in space, both of them. So this is what we developed here. We wanted to develop the all-around system. We ended up with developing a laboratory scale system. And our next steps will be working on this technology to be implemented also in an open field. So what it does here, we using camera equipped with polarized linear polarization filters, because the light reflecting from the water surface, some of it reflects at a known angle, and it undergoes linear polarization. And the amount of this linear polarization, we know from physics, is directly related to the local slope of the water surface. So the idea was measure the linear polarization, right? Get the slope, integrate over the space and time, and get the solutions. Not simple to implement. So it all went through some neural networking solution. We used deep networks. We showed here that we can create these solutions using regression type networks and classification type networks. All the way we somehow find out that the classification type networks, the layers in them before the final one, can actually give us information about faulty data, which is a very important question in this type of measurement. So, for example, you're a ship, right? Equipped with a sensor system. You're looking forward and you're trying to navigate efficiently. But you have to know which of the data that you're actually processing here is good and which is faulty. It's a visual data. So the classification networks also allowed us to classify the faulty data correctly, to identify it. I don't know why the video is not running. It's supposed to run. How many minutes do I have? 1, 2? Whatever. Okay. So you see, for example, here we see some waves are breaking. They're very steep, and then we don't have a reflection. So it's a faulty data, right? So our network is not only producing the measurements, here's the recreation, but also on the way, automatically, not autonomously, detects which data is false, which is really great. The second example that I wanted to show you is, I love focusing a lot of breaking of waves. It's a very important phenomenon because the energy of the wave field is being constantly redistributed. The wave field obtains energy from the wind. This energy appears in different waves, and then the breakings of waves redistributes this energy in other waves, to sound, to heat, and to the turbulent motion of the water. Also, waves apply forces, which is important for us for the applications I mentioned, and breaking waves apply increased forces. So we're very interested in understanding how waves break, why do they break, and how the breaking mechanism redistributes the energy. And the main requirement to do this research is to be able to access any wave field and to detect all breaking waves. And it didn't exist until recently. So recently, people were using photography, some image processing, and detecting only the most powerful breakers who generate white caps, right? In Hebrew, sometimes we call them bulbulim, this foam on the water. However, it posed a significant undercount of all breaking waves in any field, by between 30 and 60%. So we developed a new method, which uses a simple probe in the water field that creates time series. From this time series, we produce a signal which is called the instantaneous frequency through some Hilbert transform shenanigans. And I noticed that all breaking waves will create this very particular form when they pass my sensor, right? So it became a pattern recognition problem, which we solved in this case using wavelet transform and some statistics. We're reaching very high positive detection rate very low negative detection rates, and we already have publications where we implement this in the field and in the lab, and we are currently working on continuation. You see here some additional waves breaking, they're very different. These are on the shore, these in deep water. So we started listening to the acoustics of breaking waves, trying to relate the amount of noise and the type of noise generated with the type of the breaker. There's a huge classification of breakers and its intensity. Signals are not trivial. We started working on this, right? The splash makes a sound. The ripples make a sound depending on the frequency depends on the diameter, and the system moves and interacts with each other. So this is what we're working on now, basically augmenting the breakers detection algorithm with the ability to classify the breakers and to estimate their intensity. So, thank you.